All right, let's dive into a classic physics problem, one that almost every student of mechanics bumps into. It's a fantastic challenge because it mashes together acceleration, moving in circles, and a really, really important limit. We're going to figure out the physics behind a car drifting around a corner. So this is what it all boils down to. Just picture it. A car, starting from a dead stop, enters a circular curve. The driver hits the gas, so it's speeding up while it's turning. The big question is, how far can it actually travel along that curve before the tires just lose their grip and it starts to slide out? That's the puzzle we're going to solve together today. Now, the specific problem we're going to tear apart today comes from the famous Irodov collection, problem 1.90 if you want to work it up. And if you know Irodov, you know these problems can be a little tricky, but they are absolutely perfect for making sure you really get the core of physics. So let's set the scene. Okay, here's what we have to work with. First, the car has a constant tangential acceleration, we'll call it WT, of 0.62 meters per second squared. Basically, that's the engine pushing the car forward, making it go faster and faster. It's driving around a circle with a radius, r, of 40 meters. Now, the grip, that's given by the coefficient of friction, mu, which is 0.20. And finally, super important, the car starts from rest, so its initial velocity is 0. These are all our ingredients. Okay, here is probably the biggest pitfall for a problem like this. It's so easy to think of acceleration as just one thing, one number. But to get this right, you have to understand that the car is actually experiencing two completely different types of acceleration happening at the exact same time. Let's break them down. So on the left, you've got tangential acceleration, WT. You can just think of this as the go faster acceleration. It's all about changing the car's speed. In our problem, it's caused by the engine, and it's a constant 0.62. But then on the right, you have the normal acceleration, Wn. This is the turn acceleration. Its only job is to change the car's direction, keeping it on that circular path. And here's the crucial part. This one is not constant. Why? Because the faster the car goes, the more of this turn acceleration it needs to keep from flying off the road. So what's causing that normal or turn acceleration? Well, anytime something moves in a circle, there has to be some kind of force pulling it toward the center. We call that the centripetal force. For a planet going around the sun, that force is gravity. For a ball on a string you're swinging around, it's the tension in the string. And for our car on this flat track, it's all friction. The grip of the tires on the road is the one and only thing providing that crucial inward pull. So we figured out that friction is the hero here, right? It's providing the force we need to make the turn. But, and this is a huge but, friction is not infinite. It's a limited resource. It can only pull so hard before the tires just let go. And finding that exact breaking point is the whole game. If you only remember one thing, let it be this. This is the key that unlocks the entire problem. The car will begin to slide at the precise moment that the total force it needs to both speed up and turn becomes just a tiny bit more than the maximum force that friction can possibly provide. Our entire job is to find that tipping point. So, how do we calculate that maximum possible friction force? Well, the formula is pretty straightforward. It's the coefficient of friction, K, times the normal force, N. Now, on a flat surface like our track, the normal force is just the force the ground exerts to support the car's weight. So it's equal to the mass of the car, m, times gravity, g. That gives us our final formula. The maximum friction is K times m times g. This number is our force budget. We cannot spend more than this. This brings us right back to the main event. We know friction has a limit. We know the car needs force to speed up, and it needs force to turn. So what is the exact physical condition that tells us, okay, now it's going to slide? And here it is. The slide happens when the total demand for force is bigger than the supply from friction. And notice that word, total. It's not just the turning force. It's the combination of the force needed to go faster, the tangential force, and the force needed to turn, the centripetal force. Since those two forces are at right angles to each other, we're going to have to add them together like vectors. All right, we've done all the conceptual heavy lifting. We get the physics of what's happening. Now it's time for the fun part, translating our ideas into the language of math so we can actually get an answer. Let's walk through this step by step. First, we set our limit. The moment sliding begins is when the total required force exactly equals the maximum available friction. Since the tangential and centripetal forces are perpendicular, we use the Pythagorean theorem to find that total. Next, we substitute in the actual physics formulas for those forces. And here's something really cool.
Notice how the mass of the car, m, appears in every single term? That means we can cancel it out completely. The final distance doesn't even depend on how heavy the car is, which is pretty wild. Step 3 is the clever part. Our velocity v is always changing. We need a way to relate it to the distance the car has traveled, s. We can use a basic kinematics equation for that. And finally, step 4 is just algebra. We plug our expression for velocity into the main equation and solve for the one thing we're looking for, the distance, s.
So after all that work, we've derived our master formula. Now comes the really satisfying part, plugging in the actual numbers from the problem to find our final distance. And here it is. This is the beautiful result of all that physics and algebra. This one equation ties together the radius of the circle, the grip of the tires, gravity, and the car's engine power to tell us the exact distance, s, where things go sideways.
So let's run down the list and plug in what we know. The radius r is 40 meters. Our coefficient of friction, mu k, is 0.20. The tangential acceleration, at, is 0.62. And for g, the acceleration due to gravity, we'll use the standard 9.8 meters per second squared.
You run all those numbers through your calculator, and boom, there's our answer, 60 meters. The car can accelerate along this curve for exactly 60 meters. At meter 60.1, the combination of its speed and its constant acceleration demands more grip than the tires can possibly provide, and it's going to start to slide. So, what's the big takeaway here? What's the main idea to really hold on to? It's that you have a friction budget, and the car is making 2 withdrawals from that budget at the same time, one for speeding up and one for turning. The car slides when the sum of those 2 demands finally overdraws the account. It's all about that combined force overwhelming the limit of the tires. And that pretty much wraps it up. We've solved it. But I'll leave you with one last thing to chew on. What would happen if this track wasn't flat? Like on a NASCAR oval where the corners are banked? How would that change our force budget? And how would it affect the final answer for the distance? It's a great next step to think about. Thanks for joining me.